Voltage source converters based high-voltage DC transmission systems play an important role in power systems. The half-bridge-based modular multi-level converter is the state-of-the-art building block for HVDC. Typical HBMMC has DC fault blocking limitations. When a DC fault happens, the fault current rises quickly due to the low DC side impedance. Also, the MMC submodules are blocked for protection, and the freewheeling diodes of submodules act as a rectifier. Therefore, the DC fault is fed by the AC grid. DC fault protection of MMC-based HVDC is an essential area of study. The potential protection technologies include the use of fault-tolerant converters, AC side circuit breakers, and DC breakers. But such technologies need further improvement and development to implement in the power systems due to their corresponding disadvantages regarding losses and operating speed. Use of DC breakers for HVDC protection needs further investigation. Unlike the AC system, there are no zero crossings of the current in HVDC system. Therefore, the mechanical breakers for HVDC are slow due to the additional commutation circuits. Moreover, solid-state breakers with power electronic switches are fast, but this comes at the expense of high conduction losses. The most promising solution is a hybrid DC breaker built combining a fast mechanical breaker with a semiconductor branch and an energy absorption branch. The commercial hybrid DC breaker are under testing stage. Let's look at the operation of hybrid DC breaker. In the closed position, current flows through the mechanical breaker, and when a fault happens, the current would be commuted to the secondary branch by switching off the mechanical breaker, and then be absorbed by the arrestor by switching off the solid-state breakers. My objective was to implement the hybrid DC breaker control function in a DSP controller and to interface it with a benchmark HVDC system implemented in a real-time digital simulator. In this project, hardware-in-the-loop simulations with RTDS is used to test the DSP circuit breaker controller without connecting it to the real HVDC system. RTDS provides flexibility for HiL testing, including high level of safety, saving time and money. The HVDC system with DC breakers is simulated in RTDS. The DSP board interfaced with RTDS via digital and analog cards runs the program for breaker controller. At each time step, the DSP controller receives the current measurements from RTDS analog outputs and decides the next state based on the present state and current measurements. Then the DSP controller delivers the switch control signals to the DC circuit breaker via RTDS digital inputs. This is the RTDS simulation runtime. The plot from RTDS shows the fault current elimination operation. This allows the circuit breaker to limit the DC fault current in a predefined range by switching on and off the main breaker. If the fault is still prevailing, the breaker will be opened after doing FCL operation for 3 times this. And if the fault is clear during the operation, the FCL will stop and the breaker will reclose. The figure shows how the circuit breaker deals with a long fault. Circuit breakers do open, delay, and reclose operation for 3 times this and be opened permanently. And if the fault is cleared during the operation, the breaker would reclose to normal operation. In the testing at the lab, this implementation eliminates the need for an additional RTDS rack to run the protection algorithm, allowing the average model of the HVDC system to run in a single rack and the switching model to run in 2 racks.